Dear students, in this video let us study about BIOT SAVART law and the application of this BIOT SAVART law in calculating the magnetic field due to a long state conductor carrying current, and also to calculate the magnetic field produced along the axis of the current carrying circular coil. Now let us study about BIOT SAVART law. Soon after OS's discovery, both Jean-Baptiste Biot and Felix Savart in 1819 did quantitative experiments on the force experienced by a magnet kept near the current carrying wire and arrived at a mathematical expression that gives the magnetic field at some point in space in terms of the current that produces the magnetic field. This is true for any shape of the conductor. Now we see about the definition and explanation of this Biot-Savart law. So this is a current carrying conductor, and we are considering a small element dl, and a point P is considered at a distance r from this current element. And this radius vector makes an angle theta with the conductor. Biot and Savart experimentally observed that the magnitude of magnetic field dB at a point P here at a distance r from the small element length taken on a conductor carrying current varies directly as the strength of the current I and directly as the magnitude of the length element dl, directly as the sine of the angle theta between dl and r, and also inversely proportional to the square of the distance r between the point P and length element dl.
Hi, I am Jean-Baptiste BIOT. I and Felix Savart experimentally observed that the magnitude of magnetic field D at a point P at a distance r from the small elemental length taken on a conductor carrying current varies directly as the strength of the current I, directly as the magnitude of the length element dl, directly as the sine of the angle between dl and r, inversely as the square of the distance r between the point P and length element dl.
Combining all this, the expression can be written as dB proportional to IDL sin theta by r square. And introducing a constant k, we can write this as dB equal to k into IDL sin theta by r square. Now this constant k is given by mu naught by 4 pi in SI units. And in vector notation, this expression can be written like this: dB equal to mu naught by 4 pi IDL cross r unit vector by r square. So here the vector dB is perpendicular to both IDL, pointing the direction of current flow, and the unit vector r directed from dl toward point P. So this is the direction of the magnetic field using right hand rule. So if this is a current element IDL, magnetic induction will be in this direction, and IDL r is the distance. Then the equation 3.34 is used to compute the magnetic field only due to a small elemental length dl of the conductor. The net magnetic field at P due to the conductor is obtained from the principle of superposition by considering the contribution from all current elements to IDL. So we have to integrate the equation 3.34, and therefore we get this expression d equal to integral dB, which is given by mu naught I by 4 pi integral dl plus r unit vector by r square, where this integral is taken over the entire current distribution. Now let us consider the following cases. If the point P lies on the conductor, then theta equal to 0, therefore dB is also 0. But if the point lies perpendicular to the conductor, then theta equal to 90 degrees, therefore dB is maximum, and is given by this expression dB equal to mu naught by 4 pi IDL by r square n cap, where n cap is the unit vector perpendicular to both IDL and r. Here we are using this IDL vector. Why this is denoted by a vector? That is because the electric current flowing in a small elemental conductor should be a vector quantity, because the electric current in a conductor has a direction of flow, but the electric current is not a vector quantity, it is a scalar quantity. Next, we are going to study about the similarities between the electric field from Coulomb's law and magnetic field from BIOT SAVART law. The electric and magnetic fields obey inverse square law, so they are long-range fields, and they obey the principle of superposition and are linear with respect to source. So in magnitude, E is directly proportional to Q, and B is
Now let us study about the magnetic field due to a long
Here are
straight
the
conductor
differences between the
which
electric
carries
field
current.
and magnetic field
These are the
from the
applications of BIOT
Coulomb's
SAVART
law and
law.
BIOT SAVART law.
This one is the first
Electric
case.
field that is produced by a scalar
Here
source,
let us
that is an
consider
electric charge,
a
whereas
long
the
straight
magnetic field
conductor
is
which
produced by
carries
a
the
vector
current
source,
I.
that is
The
current element
center of the
df.
conductor is O. The
And
conductor is
the
Y,
electric field is
dash.
directed along the position vector
And
joining
we are
the source
considering
and
a
the point
point
at
P
which the
which is
field
at a
is
distance
calculated.
V from the
The
center
magnetic
O.
field is directed perpendicular to the position vector R.
Now we
and
are
the current
considering
element
2
df.
points A and B.
The electric field does not depend
And,
on
that
angle,
is the
but
current
the magnetic
element
field
df.
depends on the angle between the position vector
df.
R and the current
Current
element df.
I goes through this small element df. Now this YY dash is an infinitely long straight conductor. I is a steady current which flows through the conductor as shown. In order to calculate the magnetic field at a point P, which is at a distance A from the wire, let us consider a small line element dl, which is the segment AB. The magnetic field at a point P due to a current element IDL can be calculated from BIOT SAVART's law, which is given by dB equal to mu naught by 4 pi IDL sin theta by r square n cap, where n cap is the unit vector which points into the page at P. Theta is the angle between current element IDL and the line joining DL and the point P. R is the distance between the line element at A to the point P. And applying trigonometry, draw a perpendicular line from A to BP. That is shown in this figure, and in triangle ABC, this is ABC, sin theta is given by AC by AB. So, well, AC is given by AB sin theta, but AB is given by DR. Therefore, AC can be written as DL sin theta. And d phi is the angle subtended between AP and BP. AP and BP, the angle is d phi. So the measure of angle APB is equal to measure of angle APC, that's given by d phi. So in the triangle APC, we have sin d phi equal to AC by AP. But this d phi is a very small angle, therefore sin d phi can be written as d phi. But AP is given by R. Therefore, AC can be written as R d phi. Since AC is equal to DL sin theta, that can be written as R d phi. So, dB can be written as mu naught by 4 pi I by R square into R d phi n cap. And that's equal to mu naught by 4 pi I d phi by R into n cap. If phi is the angle between AP and OP, then the triangle OPA, this OPA, cos phi is written as OP by AP, that's equal to A by R. So, R is equal to A by cos phi, and dB equal to mu naught by 4 pi I by A in I by A by cos phi into d phi n cap. Here dB can be written as mu naught I by 4 pi A, and here you can write cos phi d phi n cap. The total magnetic field at P due to the conductor YY dash is given by this expression B equal to mu naught I by 4 pi A sin phi limits minus phi 1 to phi 2 n cap. So the above equation can be written as B equal to mu naught I by 4 pi A into sin phi 1 plus sin phi 2 n cap, and for infinitely long conductor, theta phi 1 equal to phi 2 equal to 90 degrees. Therefore, the expression can be written as B equal to mu naught I by 4 pi A into 2 n cap plus given by B equal to mu naught I n by 2 pi A. This is an important equation, and this will give you the magnetic field at a point due to a long straight conductor carrying current like this. Then the next application of BIOT SAVART's law is the calculation of magnetic field produced along the axis of the current carrying circular coil. Further, let us consider a current carrying circular loop of radius r, like this. And I is the current flowing through the wire in the direction as shown in this figure, like this. The magnetic field at the point P on the axis of the circular coil at the distance z from the center of the coil O is computed by taking two diametrically opposite line elements of the coil, each of length dl at C and D. So let R be the vector joining the current element IDL at C and the point P. So here points are C and D. This is the center O, separated by distance R. This is the coil of radius R. And you are considering a point P along the axis of the current carrying circular coil. Then by BIOT SAVART's law, the magnetic field at P due to the current element C is given by dB equal to mu naught by 4 pi IDL cross R by R square. The magnitude of dB is given by dB equal to mu naught by 4 pi IDL sin theta by R square. That's equal to mu naught by 4 pi IDL by R square. Theta is the angle between IDL and R, and here theta is about 90 degrees. The direction of dB is perpendicular to the current element IDL and CP. Therefore, it acts along PR perpendicular to CP. The magnitude of magnetic field at P due to current element at D is the same as that for the element at C because of equal distances from the coil. But its direction is along PS, like this. And here it is along PR. The magnetic field dB due to each current element is resolved into two components, namely dB cos phi along y direction and dB sin phi along the z direction. The horizontal components cancel out while the vertical components dB sin phi k vector, unit vector alone contribute to the net magnetic field B at the point P. So these horizontal components dB cos phi and dB cos phi, they are opposite in direction, therefore they cancel out each other. Only this dB sin phi will contribute to the magnetic field. So this B is given by the integral of dB vector, that's equal to dB sin phi k unit vector, and that is given by mu naught I by 4 pi integral dl by r square sin phi k unit vector. So from the triangle OCP here, sin phi can be written as r by r square plus z square power half, and r square equal to r square plus z square. Substituting this in the equation, we get B equal to mu naught I by 4 pi into r by r square plus z square 4 power 3 by 2 k unit vector integral dl. So if we integrate the line element from 0 to 2 pi r, we get the net magnetic field B at the point P due to a current carrying circular loop. So B is given by mu naught I by 2 into r square by r square plus z square whole power 3 by 2 k unit vector. If a circular coil contains n number of turns, then the magnetic field is given by B equal to mu naught Ni by 2 into r square by r square plus z square whole power 3 by 2 k unit vector. If the magnetic field at the center of the coil is given by B equal to mu naught Ni by 2r into k unit vector, as z equal to 0 here.